Section D is about classifying high and low points. So we call these stationary points. Think of it as kind of like we're going to be, so the big thing I want you to write here, a stationary point occurs where the derivative is 0. It could be one of three things. Local max. So a high point, it's kind of like you're going up and you're almost like it's suspended and then comes back down. So think of the stationary means it's not going up or down, it's stationary for just a brief second. It could be a local min. So you're going down still for a second, then go back up. Or we have an inflection, stationary inflection. And that looks like this. All right. So, and the stationary point, the tangent is horizontal. So 0 slope. 0 slope. 0 slope. Okay, so now on the next page, this is giving us a picture, and I didn't write, these are actual points. Point A is the global minimum because it's the lowest or minimum value on the entire domain. So in the entire graph, there is not a single point that's below this point. Now, do you see how this point here, there's a 0 slope, horizontal tangent line, in just this little area? Like if you can draw a circle and it's the high point in that area, that's going to be, it's like the top of a hill. Top of the hill is a local max. But that means it's highest point here, but there's still other points on the graph that are higher. So it's a max in that local area. Same thing here. The bottom of a hill, this is a local min because it's the smallest value in that circle there, but there's other values over here that are below. Then point D is a global maximum because it's the maximum value of y. We're always talking about the y value on the entire domain. So these are your global max and mins, local max and mins. So where you see maximum and minimums, there's two places you can see them. They can occur at the endpoints. Notice in this case, they were both endpoints, or where the stationary points, where f prime equals 0. These are the two things we've got to look for. All right. We also have to be careful that it's not a stationary point, because notice here we have a 0 slope tangent, but in that area, there's points lower and higher, so it's not a max or a min. We call it a stationary inflection point. So maybe just draw this picture. And what I wrote is the derivative equals 0. But notice it's always increasing. So it's positive on each side. So if it's always increasing, it's not a min or a max. So this we have to watch out for. If it's positive on both sides or negative on both sides, then it's a stationary inflection. All right. I didn't even use this, so we'll just keep going. All right, so this is how we're going to use our sign diagrams. So we're going to put where our f prime equals 0. So this is always where it's equals 0. I actually draw this picture on top of my sign chart. This says it's increasing, 0 slope, decreasing. So you can see that it's a local max. It's the highest point if it goes up and then down. On here, this is decreasing, then increasing, decreasing, increasing. So you can see this point is the bottom of a hill, the local min. Then if it's increasing, increasing, not a max or a min, stationary inflection, decreasing, decreasing, stationary inflection. So this is what I was just saying before. We have to find all values where the derivative equals 0, and then we do a sign diagram of f prime and decide is it a local max, a local min, or stationary inflection. So we start with the derivative. F prime of x equals 3x squared minus 6x minus 9. You've got to be good at factoring now. To find where f prime equals 0, there's a GCF of 3. Factor out the 3. Bring down the 3. Now we need 2 parentheses. X squared breaks into x and x. Factors of 3 that subtract to get 2. Minus 3 plus 2. So we have 2 x's. We have to find where they each make each one 0. Here, positive 3 makes this factor 0. Negative 2 makes this one equal 0. So these are what I'm going to put on my sign chart. Negative 2 and 3. And these are both 0 slope where it equals 0. So then we're going to plug in, say, negative 3 back in here. Negative 3, that's negative, negative. So that's a positive, because a positive times a negative times a negative. Then I'm going to plug in 0. Here, does it help if I do this? When I plug negative 3 in, I get 3 times negative 6 times negative 1. That's what's a positive value. I don't even care about the number. I just want to know, is it positive or negative? When I plug in 0, I get 3, negative 3, positive 2. When I multiply these, that's all negative. And if I plug in 4, I get 3 times 1 times 6. Everything's positive. Now, watch what I'm going to do. I'm just going to draw a graph directly on this. Positive, so it's increasing, 0 slope, decreasing, 0 slope, increasing. Does this shape make sense for a positive x to the third? Yes. So this is what the shape is. So then to find our stationary points, we have this particular point here, negative 2, but then we have to plug it back in. See how this is the top of a hill? Top is a max. So we have a max of hang on a minute. Why, see, if you guys would have been here, you would have said, Platy, you can't multiply. That should have been a 1 way back here, huh? That's why somebody printed something off and I got distracted. I'm sorry. That, yes, you're not losing your mind. That was me. All right. So -1, when we plug that in, the y value is 10. How do I find a y value? Where do I plug -1 in to find the y value? Back here. I have to plug -1 in for each of my x's, and I get a positive 10. Then what is this point? See how this is the bottom? That means, and I really should put locals here because this is going to be way lower and this is going to go way higher. That's why these are local max and mins. And the min occurs when x is 3. And if we plug 3 in to my function up here, in for each of my x's, I get -22. Okay? So these are my final answers. All right. I'm going to tell you right now, this one's a little tricky derivative, but we can do it. Why is it tricky? I have x minus 2 being multiplied times e to the negative x. So this is a product rule. So to find y prime, I'm going to take the first u, x minus 2, times the derivative of e to the negative x, which is just e to the negative x, times the derivative of negative x, which is -1, plus e to the negative x times the derivative of x minus 2, which is just 1, so you don't even really need it. So the derivative itself is not awful, but we need to simplify this because this is a hot mess. All right, so the first thing I'm going to do is I'm going to take this -1 and distribute it through here. Because I want to separate this e to the x here from the rest of the problem. Then this is just e to the negative x. All right, so in our factoring, if I look at this whole great big term and this one, notice there's a GCF. So I'm going to set my derivative equal to 0. I'm going to factor the GCF of e to the negative x out of each of these. So if I divide each one by e to the negative x, I'm left with -x plus 2 plus e to the negative x divided by e to the negative x is 1. Okay, now simplify here. Now, e to the negative x can never be 0. So the only time this whole equation will equal 0 is when this part equals 0. And I do see this a lot when we see e to the x in the derivative. So when does this part equal 0? When x equals 3. So this is our only possibility of a max or a min. So let's think about our number line. We're going to put in 3. And so let's pick 2. And e to any power is always positive. So if I plug in 2, I get -2 plus 3 is 1. So that's a positive. Then I'm going to plug in 4. E to the x is always positive. -4 plus 3 is negative. So this is increasing, decreasing. So this is a local max. When x is 3, and I just plug 3 back in, how do I find the y value? I have to plug it back into the y equation. So 3 minus 2 is 1 times e to the -3rd is just e to the -3rd. And you can just leave it that way. All right, last example. Now they give us endpoints. So we're going to just see a part of the graph. So we start the same way. Find the derivative. Set the derivative equal to 0. So there's a GCF of 3 and x. Factor out the 3x. So my two x values that make the equation equal 0 are 0, because 3 times 0 would be 0, and 4. All right. So on my number line, I've got 0 and I have 4. I'm going to actually put -2 and 5. Notice it's in between -2 and 5, but it can be equal to. So I'm going to keep these as solid lines here. All right, so if I plug in -1, that's going to be a negative times a negative, which is a positive. Plug in +1. Positive times a negative is a negative. 4.5 is positive, positive, positive. Okay. Now what I'm going to do, I want to figure out my y values. So what I'm going to do is I'm going to plug in each of these points, both my endpoints and my stationary points, into my equation. And when I do that, when I plug -2 in, I get -27. When I plug in 0, 0 is the easiest one. It's just 5. When I plug 4 in, I get -27. And when I plug in 5, I get -20. So let's think about what these points on the graph look like. So -2 is at -27. 0 is at +5. 4 is at also -27. See how these are at the same level? And this point is just a little higher. So it's increasing, decreasing, increasing. So this is the shape we're looking at. So we see the greatest and least values. This is my greatest value is 5, and my least value is -27. So you could say the greatest value occurs when x equals 0, and the least value occurs when x is -4 or -2 and 4. But if it just wants the values, the values are y values.